In the late 1800s, physics looked finished. Motion followed Newton's laws. Heat and light seemed explainable with the same steady rules. Measurement felt like reading a thermometer. You checked what was already there. If two scientists looked carefully enough, they expected the same answer, because reality was assumed to sit in place, waiting. Observation mattered for accuracy, not for the thing being observed. That assumption held everything together. Then problems appeared at the smallest scales, where classical ideas should have worked best. One involved blackbody radiation, the glow from heated objects. The known equations predicted the wrong distribution of light, especially at higher frequencies, and the mismatch grew worse as measurements improved. Another involved the photoelectric effect. Light hit metal and electrons came out, but not in the smooth, gradual way classical waves suggested. The facts refused to cooperate. These anomalies did more than embarrass a few formulas. They hinted at a deeper crack in the old picture. The results depended on how energy was exchanged, and that exchange happened during measurement itself. The detector, the metal, the radiation, all interacting. At large scales, that interaction could be ignored. At small scales, it could not. Observation still gathered information, but it also delivered a physical push. The window started to look like a hand. Between 1900 and 1905, the pressure to explain those stubborn anomalies finally forced a new kind of thinking. Max Planck tried to make sense of how hot objects gave off light. The old rules said energy should flow smoothly, like water from a tap, but the numbers refused. Planck only matched the data by treating energy as coming in fixed chunks. It sounded like a trick. It kept working anyway. Those chunks carried a simple message with huge consequences. At very small scales, nature did not always deal in continuous amounts. It dealt in packets. That mattered because measurement depended on exchange. To register light, something had to absorb or emit energy, and now that transfer happened in indivisible steps. You could not take half a step, even if your instruments wanted to. The act of detecting already demanded a jump. Then Albert Einstein pushed the idea further to explain the photoelectric effect, where light knocked electrons out of metal. Brighter light should have meant stronger electrons, but it did not. Only the light's color mattered. Einstein treated light itself as made of individual packets, later called photons. Each packet delivered one clean hit of energy. So measurement stopped being a gentle look. It became a physical event that arrived in discrete blows. By 1911, Ernest Rutherford pushed the atom into a new shape. Tests showed that most of it was empty space, with a tiny, heavy nucleus at the center. That fixed one problem, but it opened another. If electrons moved around that nucleus like little planets, classical physics said they should steadily lose energy and spiral inward. Atoms should collapse, but they did not. Something about the atom refused the usual rules. Then, in 1913, Niels Bohr offered a strange compromise. Electrons still circled the nucleus, but only in certain allowed orbits. Not any orbit, only specific ones. In those special paths, the electron did not leak energy, even though classical thinking expected it to. The atom stayed stable because nature simply blocked the forbidden motions. Stability was no longer explained by smooth change, but by strict permission. Bohr's idea paid off when it explained atomic spectra. Those sharp lines of color atoms gave off. The lines meant the atom jumped between allowed energies, releasing or absorbing a precise packet each time. No in-between glow appeared because no in-between state existed. The measurable line became the proof of the allowed transition. What could be observed did not just report the atom's behavior, it marked the only behaviors the atom could physically have. In 1924, a young French physicist, Louis de Broglie, pushed a daring idea. If light sometimes acted like particles, then particles might also behave like waves. That claim sounded backwards, but it matched what experiments had started to hint at. It also changed the goal. Physics no longer tried to picture an electron as a tiny ball following a clean path. It tried to describe what could actually be predicted. Austrian physicist Erwin Schrödinger turned that wave idea into a working tool. He wrote an equation that described a wave for a particle, later called the wave function. It did not say where the particle was, like a map with a single dot. It gave a spread, a pattern. Then Max Born, a German physicist, delivered the turning point. The wave function meant probability. It predicted the odds of each outcome when a measurement happened. At the same time, Werner Heisenberg and Max Born built a different-looking method, matrix mechanics. It skipped pictures of motion and focused on measurable quantities and how they changed. Strangely, both approaches agreed on the same results. The message was hard to ignore. Between measurements, the theory did not provide a hidden, definite trajectory. It provided a wave of possibilities, and measurement selected the outcome that became real in the record. In 1927, a hard limit snapped into place. Heisenberg's uncertainty principle did not say instruments were clumsy and would improve later. It said nature itself refused certain kinds of exactness. If you pinned down a particle's position too sharply, its motion became harder to pin down. If you fixed its motion precisely, its position smeared out. This trade-off was not a lab problem. It was built into reality. That limit came from what measurement had to do. To find where something was, you had to interact with it, and that interaction did not just reveal information. It created conditions. In quantum mechanics, position and momentum formed a pair that could not both be fully defined at the same time, not unknown, waiting to be discovered later, not secretly exact underneath, not jointly real in the same moment. Around this, the Copenhagen interpretation took shape. It treated the wave function as a tool for predicting outcomes, and it treated measurement as the moment possibilities became a single recorded result. Before measurement, the theory offered probabilities, not a hidden track you had simply missed. The act of observing did not merely disturb a preset truth. It limited what could count as definite at once. By the late 1920s, one demonstration rose above the debates because it felt almost too simple. A source fired tiny bits of matter or light toward a barrier with two narrow openings. With both slits open and no attempt to track anything, the hits on a screen did not pile up into two bands. They built a striped interference pattern like waves overlapping, yet each arrival still landed as a single dot. One dot at a time, a wave pattern emerged. That result carried a quiet challenge. If each particle really took one route, left or right, why did the final pattern look as if it went through both? So experimenters added a way to find out which slit each one used. The details varied, but the goal stayed the same: tag the path. And the moment that setup existed, the stripes faded. The screen stopped showing interference and started showing two simple clumps, as if the particles behaved like thrown grains. The shock did not come from clumsy instruments ruining a delicate effect. It came from the rule the experiment seemed to announce. Even if the detector rarely clicked, even if the information was never read out, the possibility of learning the path changed the outcome. The wave-like pattern depended on not having which path information in principle. When that information could exist, nature acted differently. The experiment did not just reveal a choice, it forced one. By 1935, the unease had not faded. Einstein, now joined by Boris Podolsky and Nathan Rosen, pressed a sharp challenge. If quantum mechanics only gave probabilities until measurement, then something felt unfinished. They built a thought experiment, later called EPR, where two particles interacted and separated. The theory still treated them as linked. It looked as if measuring one immediately fixed the properties of the other. That conclusion bothered Einstein for a simple reason. It seemed to reach across distance with no time delay. The EPR argument aimed at a specific point. Either quantum mechanics missed hidden facts that already existed, or it allowed a kind of instant connection that clashed with normal expectations of cause and effect. The surprise was not just randomness, it was coordination. Two faraway results matched, as if they came from one shared script. Erwin Schrödinger responded by naming that link entanglement, and he treated it as the real scandal. To show how strange measurement now looked, he imagined a cat tied to a quantum event, neither clearly alive nor dead, until an observation happened. It was a warning. If the rules applied everywhere, then measurement did not merely reveal a state, it selected one. And with entanglement, that selection appeared to define distant reality too. In 1964, an Irish physicist named John Bell turned a philosophical argument into something physics could actually test. Entanglement sounded like a trick of language, so Bell asked a harder question. If the particles carried preset instructions, and if nothing travelled faster than light, then their shared results had to stay inside a strict numerical limit. He wrote that limit down. It became Bell's inequalities, and it meant guesses could be checked. Soon, laboratories started building experiments that treated entanglement like a measurable object. Pairs of particles got created together, then sent apart, and each side got measured in different ways. The logic was simple. If the outcomes were only revealing what was already decided locally, the numbers would obey Bell's limit. If quantum mechanics was right, the correlations would push past it. The tests kept tightening, the stakes kept rising. By 1982, Alain Aspect and his team in France ran a decisive version of the experiment. They changed measurement settings fast, while the particles were already on their way, cutting off easy, pre-arranged explanations. The results violated Bell's inequalities. The numbers crossed the line. Broad classes of local, preset realities failed. What remained was blunt. The correlation itself acted like a physical fact, revealed only in measurement. In the 1990s, a new twist landed on the old double-slit lesson. Physicists built quantum eraser experiments, where the question was no longer just whether a particle's path got measured, but whether that path information even existed in a usable form. When the setup kept which path clues available, interference disappeared. When the setup erased those clues, interference returned. The same events, a different kind of record. Then came delayed choice versions. The decision to reveal or erase the path information happened after the particle already passed the crucial point where common sense expected the outcome to be settled. Yet the data still sorted itself into two storylines. Keep the information, and the results looked particle-like. Remove access to it, and wave-like interference reappeared. The shock was timing. The control was information, not mechanical disturbance. By the 2010s, loophole-free Bell tests tightened the picture even more. Experiments closed escape routes like hidden signaling or biased sampling, and the strange correlations stayed. But causality stayed too. No usable message travelled backward in time, and no choice let anyone rewrite an already recorded fact. What changed was which pattern appeared after the results were grouped by what information was available. Observation meant selection of accessible information, not a magic retroactive force. By the time quantum experiments stopped being curiosities, engineers treated measurement as something you built, not something you merely did. A quantum system stayed delicate only until it met the outside world. That meeting, even with a tiny probe, counted as a physical interaction. Information never came for free. It arrived through a controlled disturbance, and that disturbance decided what became definite. In quantum computing, that idea became practical. A qubit held a mixture of possibilities while it remained isolated, and then a readout step forced a single result. Researchers did not just press a button to look, they designed the coupling to detectors, timed it, amplified it, and accepted the trade-off. Stronger measurement gave clearer answers, but destroyed the fragile quantum state faster. Decoherence did the enforcing. The same logic powered new sensors and new security. Quantum devices measured tiny fields by letting them slightly push a quantum state, then reading how the state changed. In secure communication, any eavesdropper had to interact, and that interaction left detectable traces because it acted like an unwanted measurement. Observation ended as a passive act. It became engineered contact with the world, used on purpose.